Assalamu alaikum. Welcome to the Road Asset Management YouTube channel. In this video, I am going to give the overview of fast falling weight deflectometer survey manual. So this manual was prepared by the JICA expert team of engineers under the project Strengthening of Road Asset Management System in Punjab province. So, in later 2023, a subcommittee was notified by the Chief Engineer, Punjab Research and Design Department, Lahore. In this subcommittee, the members from the academia, road asset management system, from field formation, and from the Road Research and Material Testing Institute were included, and they consistently reviewed this manual along with the other pavement related manual, and this manual was then updated by the JICA expert team of engineers, which we are really thankful to you, because now this manual is according to the local conditions of the Punjab network, and it is also according to the model we are using in the department, and it is also according to the survey practices we are basically carrying out here in the Punjab Communication and Works department. So, coming towards this manual, it has total 6 chapters. So, the first chapter is the introductory chapter, and Punjab is basically upgrading the ramps and needs reliable data on pavement conditions. So FFWD survey gives the residual strength information, which helps in the maintenance planning and design. So why residual strength matters? Because pavement may look fine apparently but could have the internal weaknesses. So FFWD reveals the actual load bearing capacity. And the objective of procurement of this equipment is to monitor the structural health and detect the hidden weaknesses before the failure. Not only this, it also estimate the remaining service life and provide a scientific basis for the maintenance and rehabilitation budgets. As per the structure of this manual, it covers both the practical guide for the fieldwork, and it also serves as the technical reference for the analysis and design. Now I will move to the second chapter of this manual, which is regarding the description of FFWD. It states the working principle of FFWD, in which a weight is dropped and a load is applied. Um, then basically the pavement deflects back, and this deflection is measured by the sensors. So here we can see that FFWD has two uh, level of usage. One is the project level and other is the network level. And for the project level, a closer spacing is preferred, which is about 30 to 150 meter. And for the network level, spaced testing should be 500 to 1000 meter as per this manual. So if we see this image, which is the general flow of FFWD utilization, then we see that first we have the raw field data which should be collected during the survey, and it includes deflection readings, load level applied, and air temperature and road surface temperature and asphalt layer mid depth temperature and pavement composition. And then in the next two boxes, it shows that raw values must be corrected before the analysis. So first is the conversion to reference load, that all the deflection normalized to a standard load, which is 40 kilonewton in Pakistan. And then there is the conversion to reference temperature, which says that all the deflections must be adjusted to the standard reference temperature, which is 35 degrees centigrade in Pakistan. And then we have the evaluation part, which has two level of analysis. One is the project level. It is used for the designing overlays and strengthening or reconstruction for a specific road project, and it includes back analysis, and estimation of elastic modulus, evaluation by the forward analysis, and evaluation by the conventional method. And this analysis may also be discussed in another video as well, which you will see on this channel. And then we have the network level analysis. And in the network and level analysis, we have the deflection characteristics and direct evaluation of the deflection. And this is basically network level is used for large scale network planning, like we have in the Punjab, and the prioritization and budget allocation rather than the detailed design. Now I will move to another section of the same chapter, which is the basic configuration of FFWD manual. So FFWD has three main parts. First, we have the loading device. So loading device has the mechanism which actually applies a controlled impact load to the pavement surface. So how it works, it states that there is a fixed mass or weight is dropped from a specific height, and the weight falls onto the rubber buffer system, just like a shock absorber. So, which means that it smooths the impact and transfer the load evenly to the loading plate. And the loading plate is a 300 millimeter in diameter circular plate, usually segmented into four parts to ensure good contact even on slightly uneven pavement. Then we have these standard impact load levels. So by changing the drop height and sometimes the weight, the impact force can be controlled. So in this manual, tests are run at three standard load levels. So number one is the 40 kilonewton, which is approximately 8 ton axle, Pakistan standard design load. And then there is 50 kilonewton, which is approximately 10 ton axle reference. And then this is the 60 kilonewton, which is the 12 ton axle reference. So now there is another important note which is mentioned here, which says that on the weak pavement, the actual applied load may be lower than the intended one, and on the stiff pavement, the load measured may be higher than the target, and on the slopes, the load may also deviate. So, the load must be strong enough to generate clear deflections, otherwise, we may get impossible readings like sensors from the load showing the bigger deflections than the closer one. The far away sensors may show the bigger deflections than the closer ones. So now we move to the second part of FFWD, which is the deflection measuring device. And after the load is applied, we need to measure how much and how far the pavement deflects. And this reveals the structural health of each layer. So the deflection sensors, which are basically the geophones, so they record the vertical movement of the pavement surface, and they are extremely precise. Their resolution is of 1 micrometer, or you can say 0.001 millimeter. And then we have the layout of the sensors. Sensors are placed in the radial alignment from the center of the load plate and extending outward. Here, if I go a little back, you can see that from the center of the plate, it goes outward in the radial alignment. And then there is the deflection sensor spacing. So there are typically 9 sensor setup in millimeter from the center. So this 0 is the under the plate center, and then we have 200, 300, 450, 600, 900, 1200, 1500, 1800. So this creates a deflection basin profile and the curve of how the pavement spreads under the load. So why we have these multiple distances? So these near ones from 0 to 600 sensors, they basically captures the surface plus the base layer behavior. And the far sensors from 900 to 1800 in millimeter, they capture the subgrade behavior. Now the last part of FFWD is the data capturing and recording device. So what it captures? It captures the applied load, the deflection values, and additionally it also captures the ambient air temperature or the surface temperature. And how it basically works is that the data is sent instantly to a connected computer, which basically stores the raw data and applies the automatic corrections. So it controls the FFWD operation. So this unit, I would say, that is the brain of the FFWD, and it basically link the field measurements to the analysis software. Now we move to the next section of the same chapter 2, which is the calibration procedure. So first one is the annual calibration, or we can say it the reference calibration. So it done once a year, and it must be performed by the certified technician as per the manual and with the independently calibrated reference devices. And what could be the procedure? It could be that load cell calibration are compared with the FFWD load readings against a trusted reference loading device. And for the deflection sensor calibrations, we check each sensor against the reference standards. And for the relative calibration of sensors, we compare readings of all sensors with each other to ensure the consistency. So annual calibration ensures the absolute accuracy of the system. And then we have the monthly relative calibration. So for the monthly relative calibration, it is basically done once a month or whenever a sensor is replaced. So it uses a calibration stand which is provided by the manufacturer, and then it involves comparing one sensor against the other, and all sensors must read consistently. And as per the manual, certified technicians are not required, and it can be done by the local engineers or operators. So basically, the monthly relative calibration ensures consistency between sensors during the regular use. So, what can we adapt for Pakistan as per this manual? Since Pakistan does not have the certified FFWD calibration technicians, so as an alternative approach, we basically use this method of the deflection sensor calibration. So it states that we can calibrate using the manufacturer's calibration stand, or we can do the comparison against a known deflection value, which is a reference deflection. And then we do the load cell calibration, which is calibration by comparing its output with a known calibrated device, such as strain gauge, load reference load meter, or another FFWD calibrated unit using as a benchmark. Also, it is important that this calibration must comply with the international standards as indicated in this manual. Number one is the ASTM D4694 and ASTM D4695, along with the manufacturer specifications as well. Now moving to the third chapter, which is how to use FFWD. So, a non-destructive evaluation of the pavement soundness, which indicates that FFWD measures how much pavement deflects under a load, and this shows strength and stiffness of different layers. So, it has basically two main approaches mentioned in the manual. One is the inverse analysis, which it involves layer thicknesses along with the deflections to calculate elastic modulus of each layer. And then the second approach is the deflection bowl parameters. It uses simple indices such as the SCI, which is the surface curvature index, and the PDI, which is the base damage index. and the BCI, which is the base curvature index. So larger the values of these indices in the deflection bowl parameter analysis, weaker will be the pavement as per this manual. Then in the same chapter, we have the residual strength of asphalt pavement, which says that determining how much strength remains in asphalt and base layers after years of traffic, and helps in the planning repairs without needing full destructive testing. Then moving to another section, which is the preparation of an appropriate repair plan. It includes the following steps. Number one is the identifying the repair area in which we detect where the pavement is weak or damaged. And then we evaluate the repair methods like overlay or strengthening or the reconstruction. And then we have to verify the repair effectiveness, which indicates that we have to compare FFWD results before and after the repair, and then estimate the remaining service life, which means that to predict how long the pavement will last, and then finally for the planning of long-term repairs, like prioritize the sections and optimization of the budgets. Now I will move to the chapter 4 of this manual, and it is about the site measurement procedures. So in this chapter, we start with the field survey planning, which includes confirmation of the survey objective. So what is the survey of the projective? We have to decide that if it's a network level survey, which means it can be a broad overview or having the long intervals, or a project level survey which have the detailed design and having the close intervals. So the object may also include the repair planning, structural design, or the new material testing, or some other research purpose. And then we establish the measurement interval. As I mentioned before, for the network level, it is 500 to 1000 meters, and for the project level, it is 30 to 150 meters. And then we have another step, that is the planning the measurement process, which indicates the division of the work into preparation, like the transportation and marking and measurements, which includes drops and the traffic control and cleanup. And then the typical output for a day, which is stated in this manual, is 60 points per day. Typically, it can be also 100 points per day, but realistically speaking, as per the survey conditions and the survey experience that has been carried out on the Punjab Road Network, it has been stated in this manual realistically that there are 60 points per day, which are collected as a data instead of 100 points per day. And then we have the budget planning. The budget planning for the survey includes the cost, which depends on the traffic control and transportation and staff and the analysis effort. Now there is another section of this chapter, which is the preparation for on-site measurement. And for the on-site measurement, first we have to confirm the route. So in route confirmation, first we verify the changes and exclude the structures, for example, the bridges, and then we ensure the proper referencing with distance markers. And then there is transportation, like for the short distances, FFWD can be towed, but for the longer distances, it should be transported by the vehicle. And then there is traffic control, like work in the restricted zones. For the movable lane closures are preferred, and for the it is very important to coordinate with the traffic police as well. Then there is another point, which is the test point location. So test points are selected based on the survey objective. Usual location is the outer wheel path of the slow lane, because this is where trucks mostly travel and pavement distresses appear first. However, additional points could also be between the wheel paths for the comparison purposes, and less trafficked areas to see how pavement behaves without heavy traffic loads. So proper marking of test points ensures consistency in repeated measurements and the future monitoring. Then we have FFWD setup and measurement. So the procedure includes that first we place FFWD unit at start point, then we perform the settling drop, which makes sure that load plate is in contact with the pavement properly, and then we do the test drops. So first is the specified load of 40 kilonewton standard, and then we have 50 kilonewton and 60 kilonewton reference load. So first 40 kilonewton drop is usually ignored for preloading, and then deflections from subsequent drops are then recorded as the valid data. And then the data logged per point is prepared, which includes deflections from all the sensors and changes and load and temperature and time and sensor layout. And then we finally move to the next test point. So then we have the factors which affect the measurement. There can be number of factors which can affect the measurement, which includes that not testing in the correct wheel path, load not matching the target, like too high or too low, uneven pavement surface preventing full plate contact, presence of the structures like culverts, manholes, trenches, railway crossings, and the contaminant presence like mud, debris, water, and a sloped or cracked pavement, which is the inconsistent load transfer. So all these anomalies must be flagged in the recorded data if you come across them while doing the test. Then we have the asphalt mid depth temperature measurement. So it has a procedure for the site measurement, which is quoted in this manual. And what is this procedure? It says that drill a small hole into the pavement up to mid depth of asphalt, and then insert temperature probe, which is a hole filled with glycerin to ensure good content. And then measure at three depths. So one is the 25 millimeter below the surface, and then midpoint of the asphalt layer, and 25 millimeter above bottom of asphalt layer. And then we take the average of the three. This is the mid depth temperature. However, there is an alternative method also quoted in this manual, which states that if the direct drilling is not possible, then we estimate the same asphalt mid depth temperature by using the formulas Bell equation 2 and 3, using the surface and air temperature. I will show those two equations in the later sections. Then we have the core sampling, or I would say the trial pit data. So, pavement analysis basically needs the layer thicknesses and the material properties. For new roads, design drawings are often available, but for the older roads, data is usually missing. So, what we can do is that we can take the core samples, which are the cylindrical pavement cuts, or we can do the trial pits, which are the small excavations, or we can go for the non-destructive testing method, which is the GPR, and we have already this equipment available in the department. So we can use either of these three methods for the core sampling. Knowing the true thickness and the material is very essential for the inverse analysis. That's why either of these three methods quoted in this manual, one of them should be used. Then we have the recorded data. Recorded data at each point should include the chainage, means the location, the target load along with the actual load achieved, deflection values at all the sensors, normalized deflections at 40 kilonewton, temperature means the air, surface, and mid-depth asphalt. Also the asphalt thickness and composition, if known. So, moving towards the next last section of this chapter is the data precision, which is also very important because accuracy requirement is important to ensure the reliability. So, for the peak impact load must be recorded within the plus minus 1 kilopascal, and for the deflection, it must be recorded plus minus 1 micrometer or 0.001 millimeter, and then for the temperature it must be recorded within the plus minus 1 degree centigrade. So this data precision, these are the tolerances limits, which are complied with the international standards of ASTM and ASHTO. So this is also important to ensure the data precision while using the FFWD. So this is the fifth chapter of this manual, which is the correction of deflection. So first, why the correction is necessary? Deflection is measured in the field and it is depend on the load applied, which may vary slightly due to pavement stiffness or slope. And then there is the pavement temperature, which is asphalt is more flexible at higher temperature and it is stiffer at the lower temperature. So without the correction, two sites with the same pavement strength could show very different deflections simply because of the different load or temperature. So in order to make the results comparable, correction is very necessary. So first correction in this chapter is the load normalization, which is the conversion to the reference load. And in Punjab, the standard reference load is 40 kilonewton, but the actual applied load may vary. Sometimes it is 50 kilonewton or 60 kilonewton or even slightly above or below the target. So the here we use this equation for the load normalization. So deflections are normalized to what they would be if the load had been exactly 40 kilonewton. So this formula is basically used where d dash is the normalized deflection and d is the measured deflection, and here l dash is the target standard load, or the actual measured load is basically the L. So this load normalization ensures that the comparison site across these sites are fair regardless of the load variation. Another correction is the temperature correction, which is the conversion to the reference temperature. And the pavement stiffness is temperature sensitive, which means that higher the temperature, the asphalt is softens, and the larger will be the deflections. And if the temperature is lower and the asphalt is more stiff, then the deflections are smaller. So to make the results comparable, deflections are adjusted to a reference temperature, which is the 35 degrees centigrade in Pakistan. So Pakistan standard reference temperature is 35. However, it is different from the ASHTO standards or even the standards which are followed in the Japanese standards, the standards in the Japan, because Pakistan pavements experience higher average temperature. And the method of correction here is the uh, number one is the direct measurement. As I explained before, it is that using the drilled probe temperature to measure the mid depth asphalt temperature, or we use the estimate equations using the Bell equation 2 or 3 basically, and it estimates the mid depth temperature using the air and surface temperature. So these two equations are important for the temperature correction. So now coming to the last chapter of this manual, which is the evaluation. So general evaluation flow is that after we apply the corrections as mentioned in chapter 5, FFW deflections are processed in further two pathways. Number one is the network evaluation, and then is the project level evaluation. So in the network evaluation, as mentioned earlier, they are broad for asset management and prioritization, but for the project level evaluation, they are detailed and for the design and strengthening of a specific road project. So both path use the same raw inputs, which includes the deflection, temperature, and load, but they apply different analysis depth. So number one is the network level evaluation. So for the network level evaluation, it is used for the large scales across the entire network to support the asset management. So it has the deflection characteristics, and it use the deflection indices which are directly derived from the basin. So it has this area parameter as well, which is for the overall stiffness measurement. And then it also has the uh, threshold base evaluation as well. Um, which means that it compares the indices to the standard threshold to classify the pavement from good to fair and to poor. So it basically allows the quick categorization without the detailed back calculation. And what output it basically gives is that it the condition ratings for the thousands of kilometers, um, which can be further feed into the PMS system of ramps to get the further results. Also, it has the central deflection measurement, which indicates the overall capacity. And then there is SCI, which is the surface curvature index, D naught to D 200 for the surface asphalt stiffness. And then we have the BDI. BDI is the base damage index, and BCI is the base curvature index. So these indices are directly employed to get the results for the back calculations, rather than they are basically derived directly from the basin. Now I will move towards the project level evaluation. So what this manual says about the project level evaluation is that it is used for the design and engineering decisions when a road is to be repaired or strengthened. So it has the inverse analysis or the back calculation methodology. So if I will show you here a picture, it will be better to understand it. So it has the inverse analysis back calculation using the deflection basin and known layer thickness. and it estimates the elastic modulus of each layer, which is the asphalt, base, and subgrade, and it helps identify which layer is weak, and it requires iterative computation analysis. And for the forward analysis, there is a critical responses, which includes once elastic moduli is known, it calculates the stresses and strain under the traffic load. So it predicts the fatigue life, which is the cracking of asphalt, and rutting life, which is the permanent deformation of base and subgrade. So compare with the allowable limits, it estimates the remaining service life. So these are the evaluation methodologies that have been indicated in this manual. Another methodology which is indicated in this manual is the conventional methods, which is the empirical formula. So we can also use the simpler indices like effective structural number to evaluate the pavement capacity, and they are basically easier and faster than the full inverse analysis, but they are not that precise. So what we are employing after the collection of the data using the FFWD, what we are using for the analysis purposes is the back calculation. So that's why there is a separate video you can find on this YouTube channel to understand the back calculation and the analysis of the FFWD deflection data in more detail. So this was the overview of the 6 chapters which are included in this manual. And lastly, at the end of this chapter, another interesting thing you can come across is the example of the selection of the repair method using the AI in equation. So it basically includes the inverse analysis, which means that from the FFWD deflection, the elastic modulus is calculated of each pavement layer, means the asphalt, base, and subgrade, and then we identify that which layer is weak or deteriorated. And for the rehabilitation, we replace that the layers modulus with the modulus of the new repair material, for example, the new asphalt mix. And then we do the forward analysis, which is the strain calculation. So we apply the multi-layer elastic theory, and we calculate the two critical strains under the standard load, which is the horizontal tensile strain at the bottom of the asphalt layer, which basically uh, governs the fatigue cracking, and then we calculate the vertical compressive strain at the top of the subgrid, which is the uh, governing the rutting or deformation. And then what we do this, we use this equation for the fatigue cracking of the asphalt layer. So this equation, NFA, is the number of the load repetitions, which is the wheel passes until the fatigue cracking reaches the 20%. And this epsilon naught value is the horizontal tensile strain at the bottom of the asphalt. And then we have the asphalt layer moduli, and C is basically the correction factor for the asphalt mix type, which can be computed from the equation 6.12. And then we have the subgrade rutting equation over here, and this basically have the number of the load repetitions, or I would say the wheel passes by until the subgrade rutting failure, and it has the epsilon naught value of the vertical compressive strain on the top of the subgrade. So further, using these equations, we calculate the service life calculation, which includes the asphalt and subgrade rating. And then this is further employed in the repair method selection. So this was the overview of the fast falling weight deflectometer manual, and I am very thankful for your attention. Thank you very much.